Welcome to this video. We will talk about sampling distributions. So in this unit we will begin what is called inferential statistics. That means that we're going to use samples to make inferences about population. So as a quick reminder, population, remember that refers to all the observations of the set that we want to study. So that refers to all the individuals or objects that we want to analyze. That will be the population, the whole set, the complete set. Now, a sample is a subset that we take from the population. So, if we measure a property using the population, that's called a parameter. But if we measure the property using a sample, which is a small group of the population, we call that an statistic. So, having said that, remember that the notation changes. So in the case of the parameter, if we find mu, the statistic will be x bar. So remember, mu it's the population mean, but if instead of the population we have the sample, then that's why we call it x bar. For the variance, sigma square will be the population variance, but in the case of the statistics, it's gonna be s square, and the proportion is p, the parameter, but in the case of the statistic, it's going to be p hat. Alright, so this is the notation. So remember, what is important here is parameter. It's when we measure the characteristic using the population, while the statistic is used when you don't have the population but you have a random sample. So what is the meaning of a random sample? That means that we collect the subset without following a pattern. We take the sample following only a random selection. There are no like predefined ways to collect the sample. Now, one important thing to mention is that when we collect the sample and we measure some statistics using that sample, those statistics they have variability. So let's say that we want to analyze the weight in a city, in a complete city. So if we take a sample of, let's say, 100 people and we measure the weight of those 100 individuals, then and we find the average weight of them, let's say that I'm gonna call that x bar 1, and let's say that it is equal to 69.3. Now if we take even the same sample size, but the sample will be different, then maybe that x bar for the second sample will be 71.5, and if we could pick a third sample of the same size, maybe we get something smaller, 68.7. So what I want you to notice is that we are not going to get exactly the same value. That means that the statistics they have a probability distribution, but the way we call it, it's a sampling distribution. Why we call it sampling distribution? Because those statistics are measured using samples. So we use x bar to analyze mu, s squared to analyze sigma squared, s to analyze sigma, p hat to analyze p, and we may also have the differences of two x bars. This is when we want to compare two population mean values. So for example, if you want to check like if a product is better than other product, let's say that you want to check whether two TVs brand, like which one has a higher lifetime, so the average lifetime, you want to check in which one is higher. So you will, maybe you want to perform an analysis where you check if the difference of the means is equal to 0, if they had the same lifetime, or if there is a mu that is greater than the other one. That will mean that the difference between them is not going to be equal to 0. Another inferences will be when we're comparing variances, like from two different populations, or when we're comparing proportions. Alright, one of the backbones of sampling distributions, especially of the X bar, is what we call the central limit theorem. What is the meaning of the central limit theorem? It says that if we have an original random variable, which we call x, so it doesn't matter which is the probability distribution of x. But if we start collecting samples of x, so that means that we take a sample and we measure the mean, the sample mean, then we pick another sample, which we call x bar 2, and we keep going. Now the central limit theorem says that regardless the probability distribution of x, if we have a sample size that is large means greater equal than 30, then we expect that the probability distribution of the sample means is normal. So let me start that again. So regardless the original distribution of the random variable x, if you are taking samples and the sample size is big, at least greater than 30, then the probability distribution of the x bars or the sample means is going to be a normal distribution. So this is a very powerful theorem that supports a lot of the assumptions that we make here in inferential statistics. Now, if it's normal, that means that we will be able to standardize the variable, the x bar, and of course we will make some assumptions here. Remember that in general the equation is z equal to x minus mu over sigma. That was the equation that you remember from previous unit. But now, since this is x bar, not x, so the standard deviation that we need here is the standard deviation of x bar. But that standard deviation is different. It's going to be equal to the standard deviation of x, which is the original variable, over the square root of n. That's why the equation changes a little bit. It changes a little bit because here, again, the sigma of x bar, it's equal to sigma over the square root of n. Alright, so maybe to visualize a little bit more the central limit theorem, if we have a random variable x, if the sample size is n equal to 1, then the shape of the distribution is the same as the population. Please look that this is not a normal distribution. It looks like a different distribution. It's skewed, right? It's skewed to the right. But as we start increasing the sample size, so for example, this is small to moderate, so now it tries to follow like a bell curve. But if you increase even more the sample size and you get a large, meaning greater than 30, in that case you start getting a almost a perfect symmetric normal distribution. This will be the distribution of x bar. No, this is not the distribution of x, it's different. X is the original variable, and x bar refers to the statistic that we measure when we collect samples from the population of x. So in this unit we're talking about the distributions of these statistics. Alright, so in case of x bar, we can define some cases, so depending on the conditions of the problem. So which conditions? So if x bar is the mean of a random sample of size n, and this is the important thing, if the original population it's a normal population and the variance is known, then the sample mean follows a normal distribution. That means that we can use this equation, right? The central limit theorem. So if we know, again, if we know that the original variable it's normal and the variance is known, then we can just use the normal distribution in order to find probabilities for that x bar. Here we have other cases. So even if the original population is not normal, this is case 2, even if it's not normal, but the sample size is large, meaning n greater than equal than 30. So in that case, if we follow the central limit theorem again, we can use the normal distribution x bar minus mu sigma over square root of n. We can do this because again the sample size is large. Case 3, if we know the sample variance, that means that the population variance is unknown, and the original if x comes from a normal population, then and this is assumed for n's that are small, less than 30, for n's that are less than 30, then in case 3, in this case 3, we cannot use the normal distribution, mainly because the sample size is small. The sample size is small and the variance is unknown. So if that happens, then we're gonna use the T student probability distribution. We're gonna talk about this probability distribution during our session, the online session. But just to give you an idea, it looks like the normal distribution has the same shape, but the bell is a little bit wider compared to the normal distribution. Alright, and the last case for the mean is when, even though the population distribution is not normal, but if the n or the sample size is greater or equal than 30, then it can be assumed that the sample variance is a good approximation of the population variance. Therefore, we can use the normal distribution. So what really matters is how big is your sample, right? The bigger the sample, the better, meaning that you can approximate to a normal distribution. So let's see the implications of these cases and how they can be implemented. So for that purpose, let's solve this example number 1. Alright, the example says that an electrical firm manufactures light bulbs that have a length of life that is approximately normally distributed with mean equal to 800 hours and a standard deviation of 40 hours. Find the probability that a random sample of 16 bulbs will have an average life of less than 775 hours. So let's organize the information. We know that the average lifetime of the product is 800 hours. In addition, we know the standard deviation, sigma, is 40. Now the problem is asking find the probability that a random sample of 16 volts will have an average life of less than 775 hours. So given a sample size of 16, right, n equal to 16, we're being asked about finding the probability that x bar, because they are talking about the average life, is going to be less than 775. Please notice that this distribution, this mu and sigma, are for x. These values are not for x bar. They are different. And this probability is not about x, it's about x bar, right? Now let's check first which case we can use here to get this probability. So we know that the data comes from a normal distribution, the population is normal, and in addition the standard deviation, the population standard deviation is known, 40, right? So since we satisfy the required conditions, this will be a case 1. Case 1 is normal distribution and the variance is known. Alright, so if we want to solve this problem, then we need to standardize. we need to standardize. And remember that in case 1, we can use the normal distribution. We can use the normal distribution in order to solve the problem. So let's do that. Let's do the approximation using the normal distribution so we can solve it. So let's remember that sigma changes, and therefore the z equation is going to change a little bit, right? So z is going to be equal to x bar minus mu over, this is sigma over the square root of n, right? So remember that sigma of x bar, it's equal to the sigma of x over a square root of n. So that's why the equation is a little bit different. So now we can standardize. So this is 775 minus 800 over 40 over the square root of 60. Of 16. Right? So when we solve it, we will get that this is equal to minus 2.5. Now, why we're doing this standardization? Because now we can make the following equivalence. So we want to find the probability of x bar that is less than 775. We know that this is equivalent to the probability that z is less than minus 2.5. If you go to your tables, or even if you use Excel or R, you will get that the probability is 0.20621. This is the probability that the sample mean of 16 bulbs, they are going to be less than 775. Remember, this probability is not about x, it's about x bar, because this unit is about sampling distributions. Alright, so let's check another example. In example 2, it says that a chemical engineer assures that the average efficiency of a process is 500 grams of raw material. To confirm this hypothesis, a sample of 25 products or units is drawn every month. If the value of t, this is t student, is within the following interval, then the engineer is going to be satisfied with the hypothesis. Now the question is, what will be the conclusion based on a sample with a mean of 518 and a standard deviation of 40? Assume that the efficiency distribution is approximately normal. Alright, so in this problem, if you notice, we're talking about a sample size that is less than 30, right? So even though the data comes from a normal, even though it comes from a normal distribution, we don't know the variance. Here we don't know the variance. So maybe you're asking yourself that we know the variance because here it's mentioned that the standard deviation is 40, but the problem is that standard deviation was measured using a sample. So if it was using a sample, then it's not the population. That's a sample variance. That's a sample standard deviation, to be more specific. Therefore, given those conditions, small sample size, and that the variance is not known, then we are going to use case 3, which uses the t student. Guys, again, the definition of variance unknown is not that you don't know the value. It's not just that, because maybe you're thinking, I know that it's 40, what the relevance is that you know the population variance. If you don't know the population variance, then it means that it's unknown. Even though you can measure a sample variance, it's not the same. All right. So in the problem, let's organize the information. So it's mu, it's equal to 500. N it's equal to 25. Then we know that a sample is drawn, and the sample that will be x bar, it's 518. And S is going to be equal to 40, right? In addition, we're mentioned about this interval here. We're mentioned about this interval, minus t 0.05 and t of 0.05. Now, what is the meaning of that? So let me show it to you using this plot. Imagine that we have the t student, which looks like the normal distribution, but it's wider. And we will have here one t and the other one. So this is t that has 0.05 to the right. That's an area to the right. That's the interpretation of that 0.05. Means that to the right of that value, the area, it's equal to 0.05. Same thing with the negative value. It's the same t but negative because this is symmetric. So to this area to the right, you have to the left you have 0.05. All right, so what the problem is saying is that given this information, we're going to find a t using the sample information, and we're going to check whether that t is within the central region, this region, inside the interval. So if the t that we're going to find with the sample information is inside the interval, that means that the process is under control, right? That's what the engineer says. Everything is fine. Is if the t value will be in that interval. However, if the t is outside the limits, then there is something wrong with the process, and it means that we need to check what's going on in that process. All right, so the first step here will be to find the values of t. What is the t that has an area of 0.05? To do so, you need to use the table of the t student. You need to use the table of the t student. Now, how are you going to use that table? So you need two pieces of information. First, you need the degrees of freedom. In this case, the degrees of freedom is n minus 1. So if the sample size is 25, then degrees of freedom is 24. So for the sample, if you check the table of the t student, again, you will need the degrees of freedom. And of course, you will need also the area, the probability to the right. In this case, the probability to the right is going to be 0.05. So if you go to those tables, you will find that the t that has a degrees of freedom of 24 and an area to the right of 0.05 is equal to 1.7109. So that will be the upper limit, 1.7109, and the lower limit is going to be the same value but with a negative sign, minus 1.7109. So now what we need to do is just, okay, given the sample information, let's compute t, and then let's check if that t is within the interval or not. So let's do this, the standardization. This is like a standardization, but instead of z, we're using the test Turing. We're using test Turing. So t is equal to x bar minus mu. The equation is the same as z, but instead of sigma, we have s over the square root of n. This is 518. That's x bar minus mu. That's a parameter of the process, 500. And s over n is 40 over 25. I'm sorry, will be 40 over 5 because it's square root of n. So this is 8. Then t is going to be equal to 2.25. If you notice that value, it's outside the interval because it's greater than the upper limit. The upper limit is 1.7109, and the t that we found using the sample information is 2.25. So what is the meaning of that? It means that the sample is outside the interval that was defined by the engineer. So that is suggesting that the process is out of control. There is something wrong with the process right now, because it is expected that if the condition of 500, if the mean is really 500, so we are expecting that most of the x bars are going to be located in this area, in this inner area, in that interval, right? But if it's like far from the upper limit or below of the lower limit, that indicates that the probability that the process is following the mean equal to 500 is low, that there is maybe something wrong with the process. So this is the case in this problem. So most likely the mean of the process has been affected by something and it's shifted. It's shifted right now. It's not 500. That's the suggestion that we're getting from the numbers here. Okay guys, this is everything in this first part. In the next video we will talk about sample variance and additional cases.